because it's going to be on the exam. I don't always say, well, every topic we talk about will be on the exam. But the alternating series estimation theorem will be on the exam. You will be asked somewhere on the exam to estimate your sum or to find the error. Okay, so yesterday we did an alternating series test, right? What have we down here? Ah. Yes. Probably not. You can check over there, otherwise Mrs. Hersman has them. Things get kind of messed up. You have an alternating series if the series alternates in sign. So you have this -1 to the n or n plus 1. It doesn't matter. So it has to alternate in sign. It can't go plus, plus, minus, minus. It's got to actually alternate. And I have the limit of my sequence, with just the positive terms, has to go to 0. And it has to be a decreasing sequence. And they're not going to trick you. It's always going to be a decreasing one if the limit goes to 0. It's not to say that the limit goes to 0 makes it decreasing. That's not true. You can find sequences where the limit of the sequence is 0, but it's not decreasing the whole time. I have yet to think of one, but I know that it exists. Okay, so when you add this up, I'm going to skip down here a little bit. And this is what your sum of the first n terms is. It's b1 minus b2 plus b3, etc. And if I want the full sequence, it's going to be the first n terms plus whatever's left over. And they call that the remainder, R sub n. So it's the sum of the first n terms plus whatever terms are left over. It's called the remainder. So they might ask you to estimate, they might ask you to find the error. This is the error. Because if you take the actual sum minus the sum of the first n terms, maybe it's the first 100 terms, that's equal to your remainder. When you only add up 100 terms of an infinite series, you will not have the exact sum, will you? Will you? No. Often they converge so quickly you only have to add up 3 or 5 of the terms to get really close to the sum. How do you find what's left over? You take the actual sum minus what you've added up and you get the remainder. How do you find the remainder if you don't know what the sum of the actual sum is? What it ends up being, the remainder, all these terms that add up here at the end will be smaller than the first term you don't use. So if I add the first n terms, what's the first term I'm not going to include? B sub n plus 1. That's my neglected term. The remainder is smaller than that. So if you want to find the remainder or how much you're off by, all you have to do is find the value of the first term you don't want. That's it. Seems too easy, but it is. It's really that easy. So now this one is a little different question. I want to find -1 to the n over 1, is that 1 over n factorial? Correct to 3 decimal places. Is it just mine that's goofy? Yeah. So when you're asked to do that, just write out the terms. You're going to need a calculator. And let's find out what we get. So the first term is -1 to the 0, and it's times 1 over 0 factorial. Well, we need to have a 0 factorial because we run into it often, so we've defined it to be 1. Mathematicians can do that. Why you named what you're named? Because somebody chose to do that. Could have a different name. They had different parents. Plus, that it's -1 to the first power times 1 over 1 factorial. So right now I've got what? 1 minus 1. Not very small yet, is it? Plus, and then it's going to be what? -1 to the second power, which I don't want to write, times 1 over 2 factorial. So that's going to be what? Plus a half? What's the next term going to be? What's the sign going to be? Negative. And then it's going to be 1 over 3 factorial. 3 times 2 is 6. 1/6. What's 1/6? 2.166 or something like that. Yeah, we're going to have to go to decimals. We keep going until we get the first 3 decimal places are 0, and they're not. That's 0.16. So then it's plus 1 over 4 factorial, which is 4 times 3 times 2. So that's 1 over 24. So I'm saying you're going to need a calculator. So what's 1 divided by 24? Oh, she's going to give it to me. Otherwise, I'm going to give a calculator. 0.04 what? And this was 0.16. Is it 666? Okay. So you could add these, right? You could add those. Then it's minus 1 over 5 factorial. Do you know where 5 factorial is on your calculator? So it's 5 times 4 times 3 times 2 times 1. 20 times 6. I think it's easier to go 20 times 6. What's the 120th? We're not done yet. It's not small enough. 0.0083. So now I'm probably pretty close to being corrected 2 decimal places because the zeros aren't going to affect anything. The 8 will, though, if I have to add it here because I could do a carry. Okay, keep going. This factorials converge really quickly. It's just that I'm just trying to find the error, basically. The error, the leftover terms, all of them will be smaller than that. What's the next one? 1 over 6 times 120. What's 1 over 720? Sorry, ran out of space. 001389, not good enough yet. Is that a plus or minus? That's a plus. Minus 1 over 7 times 6 times 120. Is it 5,040? I've just seen it. No, I didn't multiply it. What's that one? There you go. That's your first neglected term. Because it's not going to affect the first 3 decimal places. So all the first 3 decimal places, if you don't believe me, add them all up. They won't be affected unless I have a carry. If you want to be safe, then I would go plus 1 over 8 factorial, whatever that is. That's really tiny. Do you see how it gets small? And all of these, because there are all these zeros here, you add them up, they're less than the first neglected term. So if I add this plus all the rest of them, it's smaller than this. So you're going to see that it's just going to be a quick thing on the alternating series test. We don't have to know any of the other stuff. There's a whole bunch of stuff in there with integrals and stuff like that. We don't have to know any of that. So just ignore that in your reading. And that will give you correct to 3 decimal places. And you take the first term you don't count. That's called the first neglected term. That's your error. So you're off by 0.000198. Now that's not bad. That was 7 factorial. That was the first 8 terms because I got to count 0. So that's not bad. Only 8 terms, and you're pretty darn close to the real sum. You'll see this when you'll start applying this, and you'll see it in the practice problems, the AP problems. And I'll point it out, and you'll find out it's not that bad. You have to know this one. Okay, we did that. Now, there's 2 more tests, and I only need this one to do the last one, which is the most important one of all. It's the one you use with the factorials, or n to the n. It's highly algebraic. You guys usually like that, the last test. Okay, by definition, if you take a series, summation of a sub n, now this will be dealing with negative signs too. They don't have to alternate, but a series that has negative signs could be all positives, but then you don't need the absolute value. If you absolute value that sequence, and you find that series, which is the sum of all the absolute values, so it's all the positive terms, you make everything positive. If this converges, then the original one had to converge. We did one with a limit of a sequence. If it went to 0, yeah, we did something similar to that. And what you say is if the series of the absolute values converges, it's called absolutely convergent. You can disregard the negative signs. So let's look at example 5. Then we're going to look at one that will be different. By the way, if the sum of the absolute values doesn't converge, we don't know anything about the original one. It could still converge. Remember, this has negative signs in it. I just don't know. So what this is saying is if I take the absolute value of this, -1 to the n minus 1, over n squared. That new series, the absolute value of this series, looks like this. You know there's all these n stuff. I'm just trying to get it done. Do we know if that converges or diverges? That converges because of the what? P series. What's true about this exponent for it to converge? That has to be greater than 1. That's all it has to be. It could be 1.1, could be 1.0001. So what about the alternating harmonic series? This is absolutely convergent. And what this, all this other test is saying is if the absolute value of this converges, which this does, then that means this will also converge. Now that's an alternating series. So we could have used the alternating series test. So it's not a big deal. But when you do the ones with the sine, if you do the sine and cosine, they alternate in sign? Not always. Depends on what the setup is. Okay, ready for this one? And the last one is the one you will see on the exam. That's a guarantee. Okay. Now we know this converges, right, by the alternating series test? That's all you have to say. You don't have to go through all 3 steps. Say, oh, it's a decreasing one, it alternates in sign. You look at it, you say, it converges by alternating series test. It's sufficient. Does the absolute value of it converge? What happens when I absolute value that? What's the absolute value of negative 1 to any power? It's 1. It's 1 over n. Does that converge? Diverges. So if we know that this diverges, the absolute value, that still doesn't tell us anything about the original one. Only way we know anything is if the absolute value converges, then the original one converges. If the absolute value one doesn't converge, I can't say one way or the other what happens to the original one. It's just not absolutely convergent, that's all. I know that's a hard theorem because you have to think about that one a lot. So it says, if a series is absolutely convergent, then the original series must also be convergent. However, if a series is convergent, the absolute value of the series doesn't necessarily have to converge. Here's an example of where it doesn't. And then maybe sometime this week I'll actually prove to you why the harmonic series diverges, because I haven't done that. Okay, why do I need this? I need this for this next test, which is the ratio test, which I haven't done yet. So let's look at this one. Oh, did I miss it? Would you like some more paper so we can do this? Because we're going to have to do this. I got lots of paper. These are all my mistakes. I don't know why it's not there. Well, some mistakes I tried to fix, but I didn't. Okay, you guys, try the cosine of n over n squared. Let's list out some terms. There's 2 pieces there. It's example 7. You're going to want a big piece of paper anyway for the ratio test. I got lots of paper. Not a problem. Well, let's write this out. It's the cosine 1 over 1 squared plus it's the cosine of 2 over 4 plus it's the cosine of 3 over 9. First off, do you believe that the sequence goes to 0? What's the maximum value cosine? 1. And you could use the squeeze theorem to show that the cosine of n over n squared is less than, or you can use, not because I'm doing a sequence, 1 over n squared. This goes to 0. And if I do the absolute value of that, that'll go to 0. That's a problem. Because this is not necessarily going to alternate in sign. This is cosine of 4 over 16. Now, these are radians. How big is a radian? So let's just estimate. No? No, pi radians is 180 degrees. So if you make pi just 3, how big is a radian? 60. It's 57 something. It's about 60 degrees. So now you're doing the cosine of 60 degrees. That's positive, right? 2 radians is about 120. What's true about the cosine in the second quadrant? All students take calc. You guys know that one, right? Only the sine is positive, so this is negative. 3 radians, well, that would be 180 degrees, but we're a little short of that. Remember, it's 57 degrees. I'm still in the second quadrant, so that's negative. See how they don't alternate in sign? Cosine of 4 radians, 4 times 60 is 240, which will be down here. What's true about the cosine in that quadrant? Negative. And I'm going to bet that I get into the next quadrant. But you see, you're going around the circle. It doesn't alternate. So the only way I can do this problem is to see if it's absolutely convergent. So if this converges, if the absolute value of this series converges, then I'm okay. If it doesn't converge, then I can't make any statement about that. Then I'll have to figure something else out. Quite honestly, I can't think of what it would be. What happens to the absolute value of the cosine? That's just 1, right? So it's going to be, well, we got to be careful with that, because this is the absolute value of that. Maximum is going to be 1, right? So guess what we're going to have to do? We're going to have to use a comparison test, aren't we? Because the absolute value of the cosine of n over n squared is less than or equal to 1 over n squared, right? Do you believe that? This converges by the p-series. This converges then just by the comparison test. I don't have to do a limit comparison. You could. If it's smaller than a convergence series, it works. If this is greater than the convergence series, then I know nothing. Then I would have to do a limit comparison. If you are on the free response, yes. On the multiple choice in my class, yes, because I want to make sure that you understand what you're doing. And the only way for me to do that is for you to tell me what test you're using. And there's a variety of tests you can use. Okay, since the absolute value converges, then this converges. This is absolutely convergent. That's all there is. Let's test number 9. It's really how you deal with the series that involve negative numbers that don't alternate. Otherwise, it alternates series. I don't use it very much. It's not that common. I just use it here on this ratio test. And what this is saying is if you take the n plus 1 term, if I take the absolute value, in other words, I can ignore the negative signs. I want this to be absolutely convergent. Because if this is absolutely convergent, sigma of a sub n is absolutely convergent, then without the absolute value signs, that's also convergent. So that would be wonderful. And this is the ratio test. It's the theorem. If I ratio the last 2 terms in my sequence, yeah, that's right. You're right. You don't have this. Let's see if I can find it. How about this? There we go. Yeah, those are my early days of smart boards. Okay. What you're saying here is if you take the n plus 1 term and you look at it compared to the term right before it, if they are both, if this is getting smaller, then my sequence is decreasing, isn't it? This is equal to, this is less than 1. The sequence is decreasing, isn't it? Well, I guess, no, I'm ratioing it. I want to just ratio this. If this is less than 1, then this series will converge. Unfortunately, if I ratio these last 2 terms and I get 1, I don't know. I know nothing. That's this last one. This is the very last test. You look for these 3 things. You look for the ratio of the 2 terms. The second to last one and the last one, basically. If it's less than 1, then the series will converge. If it's greater than 1, then the series diverges. If it's equal to 1, then I know nothing. And this is the one we're going to be using a lot. It will be on the exam. So if they ask if a series converges, you're probably going to use the ratio test. You'll see. You'll see when you get in the problems. So we're going to do the ratio test. The problem is, if it's equal to 1, I don't know anything. So we're going to look at these special cases. Do you remember, does this one converge or diverge? Converges by the p-series, right? By the p-series, I can write. And this one diverges by the p-series. It's the harmonic. It's sufficient to say harmonic. Okay, let's apply this ratio test on both of these and see what happens. Now, I wouldn't use the ratio test here. First off, you're going to see what happens. So the ratio test says I want to find the limit as n goes to infinity of the n plus 1 term, a sub n plus 1 to a sub n. That's what I want to find. If it's less than 1, then this series will converge. If it's greater than 1, it diverges. And if it's equal to 1, can't tell you anything. So how do we do this? This is where our properties of exponents come in. Do I need the absolute value? No. And when you do the ratio test, you're going to find a radius of convergence and stuff like that. When you do the ratio test, just by setting up the ratio test, you get a point on the free response. It's nice. That's worth like about 5 or 6 points. So now I'm going to put in 1 over n plus 1 squared, and this is 1 over n squared. I need to simplify that. So I'm going to multiply numerator and denominator by n squared. Whoops. So I'm going to get the limit as n goes to infinity, and I'm going to get n squared over n plus 1 squared. You can multiply that out, but what is that limit? 1. So what does that tell me? Nothing. So it fails on the 1 over n squared. What do you think it's going to do with the 1 over n? You think it's going to fail? That one. That one's actually a little easier. It's the limit as n goes to infinity. Okay, so it's 1 over n plus 1, and this is 1 over n. And I'm going to multiply by n over n. Some of you may have done this enough times with these fractions that you know what's going to happen, which would be great. When in doubt, they'll multiply by the denominator, and you'll get things nicer. So it's n over n plus 1. What's true about that one? What's this limit? 1. So in one case, it diverges. In one case, it converges. So if the limit of the ratios is equal to 1, I don't know anything. That's it. So I have to use a different test. It'd be easier to use the comparison test, right, or the p-series. So that's my next slide. Okay, so let's do the ratio test. Okay, good. I was thinking about the radius of convergence. Guess we don't do that yet. Okay. Oh, yeah, that's right. So let's just do the ratio test. They might ask you if that converges. No, I'm sorry. I guess I missed a sheet. I don't know how that happened. Okay. So first, copy down the problem. And the ratio test says the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. That's what I want to look for. If it's less than 1, it converges. If it's greater than 1, it diverges. If it's equal to 1, we know nothing. Now, you have a good guess. I mean, if you look at n cubed and 3 to the n, which grows faster? No? The 3 to the n. In the beginning, n cubed grows faster. Actually, in the beginning, that's probably not true, but after you have to get past 1, if you were to do fractions, this would grow faster. But then this one will grow faster until you get to a certain point. Anybody know where that point's going to be? Where do these intersect? Just by inspection. 3. Good. Then they're the same, but after that, 3 to the n gets huge really fast. And if you think of the graph, 3 to the n is going to look like this, where 3 cubed is going to look like this. Does that make sense? Or x cubed, whatever. Okay, so we'll just do the ratio test. Now, if I do the absolute value, what's going to happen to this negative 1 to the n? It's going to go away. So it's the limit is n equals 1. Now, what I'm going to do is shortcut a little bit. It's n plus 1 cubed, infinity, sorry. N plus 1 cubed, sorry, over 3 to the n plus 1. Now, I'm going to divide by n cubed over 3 to the n, but that's the same as multiplying by the reciprocal. So it's 3 to the n over n cubed. I don't want to do all those complex fractions. Dividing by this is the same as multiplying by its reciprocal. And every single problem is the same way. You're just going to change it. Okay? Slide this out of my way. I don't have enough room. Oh, that was a nice idea. Oh, no, it's not connected. Okay. Yes, it is. Put it back to where it was. Where was it? There it is. These my old days. Okay, so let's go ahead and simplify it. This is all algebra. It's not that bad. I will give you my hints. You can do it however you would like. I don't need the absolute value because these are positive. And what I do is, n approaches infinity, I write the terms, the factors that are similar. The n plus 1 cubed is similar to n cubed. So I write it this way. N plus 1 cubed over n cubed. And the 3's, those are similar. Can I rewrite 3 to the n plus 1? 3 to the n times 3. And then it's algebra. Because what's going to happen? You're going to reduce things, aren't you? This is going to go away. What can I do with this 1/3 that's still left? Pull it out in front. So it's 1/3. The limit, you got to be careful though, as n goes to infinity of, and this is really n plus 1 over n to the 3rd power. Well, as n gets big, I don't care about the 1. What's this answer going to be? 1. So what's this limit? 1/3, which is less than 1. So this series must converge. Well, eventually you will. Eventually, it's the algebra. But when you start doing a bunch of these, you'll find out all the algebra is the same. And I know that on one multiple choice question, they had 5 of these. You had to simplify it or whatever. You had to use the ratio test on it to see which one converged. Which to me was very time consuming. I didn't like that question on multiple choice. It really actually is. Okay, so let's do this one. I'm sure the second. Oh, I think maybe I do. I don't know which is bigger, n to the n or n factorial. Well, if that's the case, then I could say divergence. But let's do the ratio test and see what we come up with. Now, n is positive, so it's the limit. If you want to be safe on the exam, I would write this out. Right, I believe so. That's what I mean. There are 2 ways to do it. But let's say you're on the test and you say, okay, anytime you have like n to the n, anytime you have exponentials that are not geometric or you have factorials, you're going to want to use a ratio test because you can't integrate that. So it's the limit as n goes to infinity. It's n plus 1. Oh, I know what this is. To the n plus 1 over n plus 1 factorial. That's the a sub n plus 1. And then what are we going to do? Multiply by the reciprocal of that. N factorial over n to the n. This is kind of like a puzzle because this is the algebra. You just have to reduce. Just. So let's write out what it means. Okay, n plus 1 to the n plus 1. What does that look like? This one, it's n plus 1 to the n times n plus 1. No, infinity. I don't know what. I know. I was not concentrating on this. Okay, do you believe that n plus 1 to the n plus 1 is this? And then what's similar to that? It'd be this n to the n. So let's put the n to the n here. And then times, well, n factorial is just n factorial. What's n plus 1 factorial? It's n plus 1 times n minus 2 times n minus 3. It's n factorial. What's going to reduce? We're going to get rid of the factorials, the n plus 1s. And now you have to be careful with this, because I know what you're going to think. This is equal to the limit as n goes to infinity. Can I write this as n plus 1 over n to the n power? N plus 1 factorial is n plus 1 times n minus 1, n minus 2, 3, 2, 1. This is n factorial, all of that. Now, well, be careful. As n goes to infinity, let's go ahead and divide that out because I can. It's 1 plus 1 over n to the n. I know some of you want to say it's 1. Does anybody recognize it? Jonathan? It's e. Which is greater than 1. So what happens to this series that diverges?
I'm done.
Put that in your notes. You need to know that one. It will be, I can't say it will be on the exam for sure, but I'm pretty sure you will see this one on the exam. That goes in your notes. And it was. And it was on the exam. Okay. You'll see it. You'll see it. Okay.
You know what? I just saw that.
Does anybody know how to do it the other way?
Spectrum for a part completion get told.
What if you take the limit of n to the n over n factorial? You guys, the easy way, well, it's not necessarily the easy way. How do you find that limit? Remember how we did that?
Oh, yeah.
And then this is n times n minus 1, n minus 2, 3, 2, 1. This is 1, but what's happening to all of these other things? These are all bigger than those denominators, so this is not 0. So it diverges. So there's two ways to do it. If you find, you always look for that. So should we write them all down? Or do you have them?
I think we know.
Okay. It's in your study guide. We only added, this n to the n is n times itself n times. And then n factorial is this. Now these reduce to 1, but this is 1 less than n. Right. So this is always greater than 1. Even if it were 1, it doesn't matter. If I get 1, what's true about the series? If the sequence does not go to 0, then it diverges. So you could have done it that way. So you're going to have some ratio test problems. And then in the next section, which was after your test, we will export some variables in and find out when we can get them to converge. So you have to know the ratio test. All of this and then going into the next sections. Especially 8.5 and 8.6. 8.7 is the Taylor polynomials. We'll do a little bit of that, and we'll spend much more effort on the free response questions, on the Taylor polynomials in the book. 8.1 through 8.4 is Monday. So it's just the convergence test. So you have time to work. I can do questions. Yeah, we can do that. There's a question here, though, in general. Let's look at some of those problems. And there's a handout in your, it's called the series test. I don't know what color it is. But that's hard. I know it's hard, but now that you got the ratio test, you can do it. So this is it on the convergence test. The next thing's... No, we still have to finish chapter 8. We get to the important stuff. 8.3, which one did you have a question on? Which problem? You want to look at 11?
Okay, I got 11. I'm talking about, like, okay, 15 through 30.
Okay, let's look at 15. 15 is an integral test. Oh, I don't want to look. This is too heavy. So 15, and actually you guys can go to the board and do this, is n e to the negative n, which is really this, n over e to the n. Is it geometric? First off, does the limit of that sequence go to 0? First question. Is the limit, it's always the first question, is n over e to the n. As n goes to infinity, is that 0? Sure, e to the x, think of it as e to the x, sorry, x over e to the x, which just goes to infinity faster, e to the x or x. You use L'Hopital's rule. Remember L'Hopital? If you get infinity over infinity, you take the derivative of this, which is 1. You take the derivative of e to the x, which is e to the x, and that goes to 0. So the sequence does go to 0, and so then I next would look for geometric. Is it geometric? No. Is it a collapsing sum? No. Is it a p-series? No. What's another one before you get to the p-series? Integral test. So what I want to do is integrate x e to the minus x. Oh, I know what the problem is. With this one, you don't know how to integrate that. So we have to skip this one, but it's integration by parts. If you do a u substitution, it's not going to work. I know. That is tricky. But did you know it was integral test? No. So, I don't remember if that converges or not. No, if this one does. You'll always check your sequence. So this is integration by parts. We'll do that later on this year. Yes. So I haven't taught it yet. You can. Well, there's more than one way to do a lot of these, so I don't know. I would just do a comparison test. It's n squared over n cubed plus 1. When I get something that looks like that, it makes me think of the p-series, doesn't it? What does this look like? If you were to ignore the 1, it looks like 1 over n. Now, here's how I would do this. I would divide the numerator and denominator by n squared. It's going to be divergent. This is 1 over n plus 1 over n squared. How does that compare to 1 over n? Is it bigger or smaller? If it's smaller, I know nothing. No, you're increasing your denominator. So the comparison test fails, but you do the limit comparison test. So I'm going to take n cubed over n cubed plus 1. I'd rather use that form, I think. And then 1 over n.
I know, but
Sorry, n. No, not yet. Not n squared. But anyway, limit as n goes to infinity. So I'll multiply by n over n. And so I get the limit as n goes to infinity. That's n cubed over n cubed plus 1. What's that limit? 1, which means they both behave the same way. their ratios of their terms are very similar. In fact, they're the same for this one. So if this one converges, 1 over n converges, this one will converge. If 1 over n diverges, the original series will diverge. But we know, let me put a little line here. This diverges, right? That's what we compared it to. So this diverges by the limit comparison test.
Uh-oh.
And it doesn't hurt you to do an assignment twice because you won't remember.
1 over divergence.
Because I couldn't do the regular comparison because this was smaller than the divergent series.
I thought it was like,
If 1 over n diverges and this is smaller than, can you say anything about it? The graph helps. Right.
so that's like, if it is convergent.
If this had been convergent, then that would have been convergent. So I'll use the limit comparison test is a better test because it'll work. Even if I don't know how it compares, then I'll do a limit comparison test.
So what are the values?
If the ratio of your unknown series, which is this one, whoops, to the known one is equal to a number, not 0, not infinity, then they both do the same thing. So if this one converges, that converges. If this one diverges, that diverges. I don't know. Then I got to do a different test. That's what you don't like. Because you're so used to math, if you do this, this is what happens. Not anymore.
If we was it's divergent by the comparison.
Limit comparison test. You'd be wrong. Had this been an n cubed minus 1, then you could do it. If this had been a minus 1 right here, then you could do it because then this would be bigger than my divergence series. So it would lie outside of this series. And since that diverges and that's bigger, that's going to diverge. Let's do some more. 17? I would like to compare it, but guess what? I don't think I can. Okay, I could argue it. I can't really use the p-series, but could you argue it? Because you really have 1 over n times 1 over the log of n. Remember, the dividing point here is 1. Anything bigger on this exponent, well, I think it converges, but I'm not sure. So I can't do that. Can't do a p-series because it's not a p-series. It's not geometric. The limit of the series sequence certainly is 0. What's the only other test I can think of easily? I suppose you could do a ratio test, but that doesn't look easy either. Let's integrate it. So it's 1 over x log of x. So what we're going to do is do a u substitution. What would you like u to be? U equals the natural log of x. So du is equal to 1 over x dx. Okay, so it's going to be, this is u, right? And the other part's du. So it's 1 over u du. If I integrate that, that's what? Marcus, what's that? ln of x is u. This is u, and these things together is du. So I get du over u. So this is the log of u, right? And we're going to go from 1 to t. Well, we have to go back first. And no, it's the ln of u, but what's u? Let's go back. It's the natural log of the natural log of x. And we're going to evaluate it at 1 and t, and take the limit as t goes to infinity. Just let me finish this thought. Okay? Now, are you confused on the integral? If u is equal to the natural log of x, I have 1 over x times 1 over natural log of x. In fact, let's put the dx here. This is the u. This is du. So I get the integral of du over u, which is that.
Oh, I got you.
Okay?
And then that one over
Natural log of u. I still don't even want to take the limit until I get back to the x's. Yes? Because I couldn't think of anything else to do. It's not a p-series. It's not a collapsing series. And integration, we didn't have these last tests alternate. It's not an alternating series. I might be able to do the ratio test, but it's not in this section. So what do we get? I was wrong. I thought it was going to converge. What do you think? No, it's not time. No, you have to fix them and correct them and hand them in. Okay, you guys, let's finish this problem. It's not time to go. This is, well, that's a problem. I get the log of 0 right there. That's a problem. And what about this? This is the log of infinity. Does that converge? No. You needed to have done 510. I assigned 510 a while ago, but that reviews how to do this. Okay, there's nothing new tomorrow, but you do have a quiz, so first we'll do questions. Quiz isn't bad, actually.
So it's 8-1 to 8-4 tomorrow.
3, not 8-4. Not 8-4. Nope, we just started 8-4. Right, and it's not bad, and you get a partner. How's that sound? Come on.